Let's review our interpolation schemes so far. Linear interpolation produces a graph that doesn't look nice and doesn't have a continuous derivative. The full Lagrange polynomial produces a graph that also doesn't look nice, but at least has a continuous derivative. The smarter cubic Lagrange interpolation produces a graph that looks great, but doesn't have a continuous derivative. Our final interpolation scheme, the cubic spline, lets us have both. For this reason, it's usually the go-to choice for physicists. To set up a spline, we need to look at a region between two data points. Let's suppose this region starts at xj and ends at xj plus 1. We'll measure our position within this region relative to xj. The cubic spline can be written as a coefficient times our position to the third power, plus another coefficient times our position to the second power, plus another coefficient times our position to the first power, plus a final coefficient. These coefficients are different in each region of data, so we'll label each of them with a j. This function has 4 unknown numbers, so we need 4 boundary conditions to solve for them. The first boundary condition is that we need the spline to pass through the data point at xj. The second boundary condition is that we need the spline to pass through the data point at xj plus 1. So far, this is the same as when we set up the Lagrange polynomial. But this time, we're going to take the first derivative of our spline and require it be the same as the first derivative of the spline in the next region when we reach the endpoint. That gives us 3 boundary conditions so far. We'll take the fourth boundary condition to be that the second derivative also has to match when we reach the next region. That's 4 equations with 4 unknowns. Well, except it's really 4 times the number of data points, giving us a long set of equations. That's exactly what linear algebra is for, so we can set up all these boundary conditions in a matrix equation. The matrix is a tridiagonal matrix, meaning all of its elements are zeros, except along the diagonal and its neighboring elements. The matrix multiplies a column vector that contains all the values of the second derivative of our spline at each data point. And the column vector on the right-hand side contains our data set. So to create a spline of our data, we need to solve for the column vector here in the middle. In this code, which is available in a link in the description below, we've set up a function that creates a cubic spline out of a set of data. First, we set up the 3 sets of elements in our tridiagonal matrix and the elements of our column vector. Then we solve the matrix equation for the spline's second derivative values. This uses a recursive linear algebra technique that you can learn more about in the references below. Then we set up lists that contain the coefficients we need for our spline in each data region. After calling this long function, we extract these coefficients and use them to set up our cubic spline in each region. The result is stunning. No kinks, no monstrous wiggles, and we still pass through every data point. Checking the first and second derivatives confirms that this spline is behaving wonderfully. It definitely looks like the cubic spline is a winner over the other interpolation schemes, but there's one additional evaluation criterion we might consider: understandability. In science and mathematics, we don't just want to compute a quantity, we want to understand its significance. It's pretty straightforward to understand the significance of a linear interpolation. It uses the rate of change of our 2 variables and the initial value of the dependent variable. The Lagrange polynomial involves many coefficients, but at least we can say that it's the one and only polynomial that passes through all our data points. Cubic Lagrange interpolation involves fewer coefficients at the local level, and you can understand those as the initial value, the slope, the concavity, and whatever the thing multiplying x cubed is supposed to mean. Cubic splines also involve a small handful of coefficients, but the relationships between them are encoded in a matrix that you feed into the computer. What do those coefficients mean? Is there some physical meaning embedded in this 50-line code or the numbers it outputs? It looks like cubic splines offer us the interpolation we want, but at the price of a straightforward understanding. Is there a better option out there that lets us have it all? Only time will tell. You should now be able to use cubic splines to interpolate a given set of data. Use the code in the link in the description below and enter the data on screen in a list. Then use the make spline function to answer the questions on the screen.